This lesson deals with supplemental problem 2.23. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems, starting on page 51. A common problem in audio power amplifiers is a thing called speaker burnout. The reason for this is that a power amplifier has a maximum output that could far exceed the rating of the speaker that it's hooked up to. For example, if you had a 60-watt speaker, but your stereo can put out 70 watts, you most likely would permanently damage it. This supplemental problem is based on a magazine article in Radio Electronics, volume 31, number 8, entitled Zener Diodes Prevent Speaker Burnout. So let's see how we're going to do that. First, could you design a circuit using Zener diodes that would give you the following VI characteristics? When the voltage begins to increase, there's no current, and at some point, current begins to flow. And likewise, in the opposite direction, we get to minus V sub x, current begins to flow. Pretty much no activity between here, and then all of a sudden this will divert the current. That's how we're going to protect the speaker. What does a plot of a speaker look like versus frequency? What I've sketched here is the impedance, magnitude, and angle of a 60-watt, 8-ohm speaker. This is what the magnitude looks like. This is what the phase angle looks like. Also, there's two frequencies where the phase angle passes through 0 degrees, besides DC. Looking to determine an equation or an expression, we're picking the Zener diode voltages to achieve this plus and minus V sub x we had on the previous page for a given speaker wattage rating. Then could you pick specific Zener diodes to provide at least 10 watts of protection for a 60-watt speaker? Look at the simplest circuit possible for achieving this result, and probably we could put two Zeners in parallel and see if that would work. These two in parallel. Now if the voltage across here is, say, 0.7, then current's going to want to flow in this direction back out this way, and this Zener won't turn on. Likewise, when the voltage goes negative, and this becomes 0.7 in this direction, current will go this way, but nothing will go this way. We'll get the curve that we want, but V sub x is going to be VD on. Let's try putting two Zener diodes in series and see what happens. Here's one and here's two. I'm going to have them opposing each other. Your current wants to flow. We would create a drop across here of VD on, and then a drop across here of V sub z. Here's my I and here's my V, and then here's my V1 and I1 for this diode, and V2 and I2 for this diode. I'm going to show it in the Zener direction for this one. Let's sketch the VI characteristics of diode 1. That's going to have a turn-on voltage at VD on, and then a Zener voltage at minus V sub Z1. And then for the second diode, when current flows in this direction, we would have V sub Z2. And when current wants to flow in their direction, we would have minus V sub D on. The total voltage is the sum of the two voltages for a given value of current. Just pick a value of current, say here, and then we'll construct an equivalent VI characteristic. For this value of current, the voltage across V1 plus V2 would be VD on plus V sub Z2. Go in the other direction. For a value of current over here, we would have minus VD on and minus V sub Z. We get this VI characteristic where we've got turn-on voltages now extended out to V sub Z plus VD on. Now let's pick V sub Z1 to equal V sub Z2. Just call that V sub Z. And now we have that V sub x is equal to V sub Z plus VD on. If you recall from ECE302, we described an impedance as having a real part and an imaginary part. Then we later went on and talked about complex power, and the real part of that complex power is what does work, or in our case, creates sound. And we used the symbol uppercase P for that, and one of the formulas we derived in chapter 16 on page 6 was this one. Now, the reactance here changes with frequency. If you pick this as small as possible, then you get the most power in the load. If I were to do that, I was make it 0, this would cancel with one of these, and I'd get that the real power is the RMS voltage divided by the real part. If you go back and look at the speaker impedances I plotted on page 51, there were two frequencies where the angle passed through 0. In other words, where x is equal to 0, besides DC. One was 60 hertz, and it was about 35 ohms at 0 degrees, and you can write that in rectangular form as 35 plus J0. And then at 300 hertz, it was roughly 8 ohms at angle 0, so you write that as 8 plus J0. Trying to get the most power out, again, from this equation, this cancels with one of these, divided by R. The smaller I can pick this, the larger this quantity will become. So I'll pick the smaller of these two as being the worst case for power. Let's solve for the RMS voltage across the speaker. It's going to be 8 times the maximum power rating of the speaker, and then take the square root. The RMS value is the peak voltage across the speaker divided by the square root of 2. It's solved for the speaker voltage as the square root of 2 times the RMS value, and then bring that square root of 2 inside here, and I get the square root of 16 times the maximum power rating of the speaker. In our case, we're going to be taking a look at a 60-watt speaker. We're looking at about 30.98 volts peak across the speaker. Voltage across the speaker is VD on plus V sub Z, so I could solve for V sub Z by subtracting off VD on. Because I have a lot of current flowing through, it's probably close to 1 volt. Suppose it's 0.98 just to make the algebra simpler. We're looking at a 30 volt Zener. Try to provide 10 watts of protection. In other words, I've got a 60 watt speaker and a 70 watt amplifier. I'm going to dump at most 10 watts into this combination of Zener diodes. So I did some web searching and found that a 1N2989 was a 10 watt 30 volt Zener. This is my final design. A couple other comments. This interconnection of Zener diodes, when current flows this way, I get VD on plus V sub Z. When current flows this way, I get VD on plus V sub Z. In other words, the negative of the other one. That's actually the same plot we had for the double clipper in chapter 2 on page 39. It doesn't look like it, but it has the same equivalent circuit. There's also another device that uses this same idea called an MOV. MOV is short for metal oxide varistor. It has the same VI characteristics as this, but the equivalent Zener voltage is about 250 volts plus and minus, and they're used in power strips to protect from lightning strikes. If lightning strikes a line far enough down, the voltage across the line will begin to increase, and if it gets too large, it can damage a piece of equipment. And what you can do by putting this device across the line is that when the voltage exceeds 250 volts plus or minus, current begins to conduct, and this will take away some of that energy. And this is supplemental problem 223.